I'm Emily Shuckburgh. I work in this department here, but my background is that I'm a climate scientist. And what I'm going to be talking to you over the next hour about is how we are using machine learning in various climate-related problems. And the way that I'm going to structure things is I thought I'll start off with describing to you a little bit of some of the questions that we're being asked to address from the climate perspective. I'll then describe to you how traditionally we've gone about modelling the climate in order to produce future predictions of climate, and then what we're starting to do in terms of bringing some of the machine learning methods into climate science. If you've got any questions, then just please interrupt as we go through and we can dive into more details and different aspects of it. So there's lots of people that have been involved in different bits of this work. There's a really growing community in Cambridge who are involved in this machine learning and climate side of things. In particular, we have a PhD program, and there's a few students here who I can see who are part of that PhD program on AI and environmental risk, and quite a number of the students part of that program are undertaking projects specifically around climate science. And then there's just a whole bunch of names, some of whom have been involved in various different parts of the work that I'm going to show who are on here. And the other organisation that I put on here, as well as University of Cambridge, is the British Antarctic Survey. I actually worked at the British Antarctic Survey for a decade or so. They're located just down the road on the West Cambridge campus, and there's a growing interest in the British Antarctic Survey about using machine learning in various different climate-related problems as well. They're involved in the CDT that we have. Right, why is this not going forwards? There we go. Okay, so just setting the scene in terms of what kind of questions are we looking to be able to respond to in terms of the science. There's a real need, as climate change is starting to hit around the world, to provide what's said here, actionable information on climate related risks. So information that can actually be used to help decisions. And actually, literally, as I was coming in here just now, like 5 minutes ago, I got an example of this because I got phoned up by the BBC who want me to be on the 1 o'clock news just after this lecture, because the UK is just about to go into a major heat wave. And so they want to know what's, all the obvious questions that you might have. What's the, are heat waves becoming more frequent than they were in the past? What's the likelihood of them becoming more frequent in the future? What's the impact of that in terms of the impact on people's lives? We know that, that anecdotally, particularly elderly people die if it gets, particularly in large numbers, because they get heat stressed. So what's the actual evidence behind that? And what should we be doing in terms of our response, in terms of should we be building our buildings differently in response to those high heats? So that's the sorts of questions that we're getting asked, and we need to be able to find ways of providing the evidence base to be able to help provide informed decisions associated with that. So that's on the one side of things. On the other side of things, we actually have we have ever increased data sets telling us in ever greater detail about all sorts of things associated with the environment, increasingly from satellites, as well as networks of sensors, either on the land, or the actual image here is actually networks of sensors that we have in the oceans. As well as from computer simulations themselves. And so how can we make better use of all that wealth of data to help inform those kind of decisions? Okay. Oh, that's computer simulations. So the bedrock of the kind of synthesis of climate information is the IPCC, the Intergovernmental Panel on Climate Change, which produces these mega reports every 5 years or so. And the last cycle of IPCC reports has just recently been produced. And I put that up there because I'm going to start to kind of explain a little bit more about exactly what's done on the climate side of things, and it's a good way of describing it. There are 3 different reports that come out associated with IPCC each cycle, and the first one is, as it says here, the physical science. So this is predominantly focused around projections of what the essentially weather is going to be like in the future. So literally looking at how the atmosphere, oceans and ice around the world change and what the response of that is in terms of extreme weather. So that's the kind of physical side of things. The middle report is called Impacts, Adaptation and Vulnerability. So that then starts to move more into the impacts on people and nature. So you've got what the change in weather is, then the next report is in terms of what the impacts of that are in terms of people. And then the third report is focused on mitigation of climate change. So that's then focused more around things like the technology or the economics of what needs to be done in terms of response to climate change. And there's modelling that's underlying each of those different dimensions, but it's modelling around slightly different topic areas. And I'll talk a little bit about what we can be doing across each of those different dimensions. Okay, so that's the kind of background in terms of what we're wanting to respond to. What tools do we have in terms of producing the response to those questions? So the absolute core of all climate modelling has been weather and climate models. And these are being developed for around about, I'll try and turn off my, it's coming up with notifications anyway. These have been developed over the last century, and at the heart of weather and climate models is solving the equations of motion for the atmosphere and oceans on a grid. So what you can see in the top right-hand corner is actually a description of the equations of motion. I mean, it's essentially Newton's second law, actually. I've highlighted the key terms within those equations, which is a balance between the Coriolis force and the pressure gradient, which is the key determinant of many weather systems. And that's encoded within climate models that have been developed over the last 100 years. The very first numerical weather forecast, as is detailed there, was produced on a slide rule back at the start of the last century. And L.F. Richardson, who was actually a student at King's College in Cambridge, made the very first numerical prediction of the weather based on measurements of pressure and wind. And as it says here, it took a very long time to produce that forecast, and it was very inaccurate. But it was the start of the idea that we might numerically be able to predict future weather. And today, we've developed that initial idea into much more sophisticated climate-related models, where on a grid, we numerically solve these equations. And as I'll come on to describe, one of the key challenges is that all the relevant physical processes that happen below the scale of the grid in which we're explicitly solving the equations of motion have to be in some way represented, parameterized within those numerical models. And so the sorts of processes that need to be parameterized within those numerical models, some of the cloud processes, which can happen on very small scales, need to be parameterized. Some of the processes associated with sea ice, again, can happen on very small scales, need to be parameterized. Some of the physics of the ocean, effectively weather patterns in the ocean happen on much smaller scales. Those processes need to be parameterized. So lots of different aspects that need to be parameterized. Typically in a climate model, the grid boxes that you have in a climate model can be as large as 100 kilometers squared, or 100 kilometers, and then in the vertical as well. And so there's quite a lot of processes that happen below that grid scale. So just in terms of the way in which climate models have evolved, after that first weather forecast, that was produced by L.F. Richardson, he then produced this amazing book, Weather Prediction by Numerical Processes, in 1922. And this was long before the initial, the first physical computers. And so he described this idea of having 64,000, he called them computers, but he was thinking of people with their slide rules, calculating the weather for different parts of the world, all sitting in their mega theatre, trying to keep up with the changing climate, changing weather in order to predict the future weather. So it was this kind of amazing idea long before we had modern day computers as to how this might happen. And then when we moved forwards to the 1950s, some of the very first applications of new computing technology as we know it now was to produce weather forecasts. And so you can see here that the first successful numerical prediction of the weather was in 1950 and used 25,000 punch cards. And that's all really evolved, but it's always been the case that some of the largest compute infrastructure has been used for weather forecasting. And this is a photograph of the UK Met Office's latest computer. In terms of the weather forecasting side of things, then the forecasts ingest large amounts of observational data to initialize their forecasts. And the code that's used to forecast the weather for tomorrow is broadly the same as the code that's used to forecast the climate over 100 years. It's just that there are different physical processes that are relevant to tomorrow's weather than are relevant to the climate in 100 years' time. So, for example, if you're looking at tomorrow's weather, what's happening in the oceans or what's happening to the ice sheets is not as relevant to what's happening to the weather tomorrow. It's really what's happening in the atmosphere that's most relevant. Whereas if you're interested in climate in 100 years' time, you do need to understand how the oceans are changing, how the ice is changing, and importantly, how those different processes are coupled together, how the change in the oceans influences the atmosphere, how the change in the ice influences the atmosphere, and the other way around as well. So it's basically the same models, but there's just different components that are included. And as you include more components of the climate system, then you have a trade-off between the resolution at which you can run your climate models, that grid scale, and the number of different processes that you can include in the models. So whereas you can run a weather forecast model at very high resolution, kilometre scale, because you include less process, it's primarily just the atmosphere. When you start to talk about a climate model, because there are many other different processes that you want to include, and because you want to run those climate models for much longer periods of time, as in real world time, over periods of decades or centuries, then you have to use a lower resolution, so more things need to be parameterized in the models. These models are super complicated. They've been evolving now over decades, and they were first written in Fortran mostly. And so what's typically happened is that they've just grown and grown and grown as this huge, complicated Fortran code. And although there's every now and again been initiatives to look at whether or not they can be translated into different coding languages, that's a mammoth job. There's one or two new models that are being developed from scratch in different languages. So there's a big project looking at developing a climate model from scratch in Julia at the moment. But for the most part, there are these horrendous Fortran codes, which most people, there's no typical climate model, no single person will have ever read and understood every bit of the code. MetaOffice model more than 1 million lines of code. And then, if that's not all complicated enough, in order to produce the IPCC reports that I just described, there's a large international coordinated effort around modelling. So each cycle of this, there's about 40 different modelling centres around the world that contributed to the most recent IPCC report. And each of those modelling groups has a slightly different climate model. There's a lot of similarities between them, so they're not entirely independent because they're all based on that same principle that I've just been describing. But they are different, and so they're different, for example, in the way that they have developed the parameterizations for those subgrid scale processes, and they're different in terms of the different processes that they choose to include or not. So they don't produce the same results. But what's the coordinated effort is ensuring that there's a common set of experiments that are agreed upon in advance, that each of the modelling centres undertake the same experiment, and then there's an intercomparison between the results of each of those experiments. And the climate context, the experiments are typically looking at different future scenarios of greenhouse gas emissions, or future scenarios of the concentration of greenhouse gases in the atmosphere, so that everyone's looking at the same future history. And the most recent example of this coordinated effort, which was put together for the last IPCC report, itself has produced more than 20 petabytes of data, which is this amazing repository of climate information, which itself can be mined as a data set to understand more about the future climate. So this is, I thought I'd show you some of the outputs of those climate models to give you a sense of what they're producing, and then we can talk about how machine learning can be used in different ways to improve this. So the results of those 40 different modeling groups, all doing the same set of numerical simulations, feeds into this figure, which comes from the most recent IPCC report, that first report looking at the physical science side of things. And if I just talk you through what these two plots show. The top plot shows the global average surface temperature that's come out of these numerical simulations. And there's two different sets of simulations that are shown on this plot. The bit between 1950 and 2015 is the historical period, where what the models are doing is trying to reproduce the climate that we've actually observed over that time period. And then the bit from 2015 through to 2100 is looking at various different future scenarios in terms of different emissions of greenhouse gases. And so those different numbers that are shown, SSP5-8.5 and so forth, are the names given to those different scenarios, different levels of greenhouse gases. So the top one, the one that's got 8.5 at the end of it, is a scenario that has a very large amount of greenhouse gases emitted. And the bottom one with 1.9 next to it is a scenario with much less greenhouse gases. So you get higher temperatures, the more greenhouse gases that you emit. The shading that you see is the range of the different results from the 40-odd different models. And sometimes there's multiple simulations of each model with, for example, different initial conditions. And so you can see that there's a spread in terms of the different models. And then the line that you see in the middle of that is just the multi-model mean of those different simulations. And so you can see that as you move out in time, you get a larger spread in terms of the uncertainty associated with those different models. And that's largely because as you move through time some of the ways in which the physics is represented in different models leads to larger differences between the models over time. So that's why you see this expanding uncertainty over time. That's the surface temperature. The bottom plot shows a different aspect of the climate models, and that's Arctic sea ice and the extent of Arctic sea ice. And what you can see compared to the temperature, you can see much greater uncertainty range between the different models on Arctic sea ice. And that's because Arctic sea ice is a fundamentally more difficult thing for the climate models to be able to represent than global average surface temperature. And so from the perspective of how we look at trying to improve climate models, then Arctic sea ice is something that we would very definitely like to try and improve, because as you can see, whereas the range of uncertainty on the temperature is sufficiently small that we can see the difference between these different scenarios of future emissions, when it comes to the Arctic sea ice, the uncertainty is so large that we can't see the difference between the different scenarios. So it's not as useful thing for us. The modelling results are not as useful. Yeah. The uncertainty is from the models. Yeah, so I haven't shown the actual observational data on here. This is just the modelling results. Okay. So that's one level. Oh no, go on. Yeah. Yeah, I can see what you mean. That's a good question. I don't know immediately what the answer to that is. It could actually, I mean, there was a big volcanic eruption in '92, Mount Pinatubo, and it could be that that's what it is. Yeah. Right, so that's one level of challenge associated with climate models. This is another level of challenge associated with climate models. And so these were looking, the top picture over there was looking at the global average temperature. But of course, for answering many of those questions that are about the relevance to people and to nature and so forth, you need to know what the local temperature is. And so you need to understand what the pattern of temperature change throughout the world is. And again, just like on the, well, I've been showing that surface temperature and the sea ice, and showing that the sea ice is much more difficult to predict than the temperature. There are other things that are very challenging in terms of the spatial patterns, and one of them is the amount of rainfall. So whereas future projections and the pattern of future projections in terms of temperature is relatively well represented by the models, getting the precipitation, the rainfall, right, is much more challenging, and there's a lot of difference between different models and their projections that they come up with in terms of rainfall. So that's the, oh yes, go on.
Is 2.6 the most likely scenario that you're doing? So like specifically you visualize from all of them 2.6. So is this the most likely scenario that you'll be in? No, that's so the Paris Agreement. So what you see over here is on the left-hand side of that plot up at the top is the temperature change relative to 1850 to 1900. And so the Paris Agreement says that we want to keep temperatures well below 2 degrees of warming, with an ambition to keep them below 1.5 degrees. So if you translate that across, you can see that the one that ends 2.6 and the one that ends 1.9 are just in that zone of keeping temperatures below 2 degrees and well below 1.5. So I've highlighted those just because those are the ones that are consistent with the Paris Agreement. They're not the ones that are consistent with what the world's doing at the moment, sadly. Okay, so that's the kind of state of the art. Then where are we wanting to go, in which directions we're wanting to go to improve on that state of the art in terms of our climate modelling responses, and then where did machine learning potentially fit into those different areas? So I've highlighted three different key developments at the moment in terms of the climate modelling. The first is that there's a big push. This is a paper that came out a week or so ago in Nature Climate Change. There's a big push towards throwing compute resource at this, basically. So the idea is that, as I was describing, one of the key challenges is that climate models have a relatively coarse resolution, lots of processes have to be parameterized within that grid. So if we threw a very large amount more compute resource at this, then could we push that resolution down and start to run our climate models at kilometre scale? Maybe instead of having 40 different groups around the world running different models, consolidate, have a few smaller number of groups running a smaller number of models at very high resolution, and that would improve the accuracy of the climate predictions. There's quite a bit of evidence in particular that if you really want to represent some of the most impactful climate features, like strong storm systems, for example, then you really do need that higher resolution to get good fidelity in terms of the output of those models. So there's a big community that are pushing for higher resolution. At the same time, so that's a focus on the physical climate, but as I described, there's that, that's only part of the pipeline towards providing information that can actually help make decisions. And so the next area where there's a lot of interest is, can we be developing digital twins of different key aspects of the real world that then feed in climate information, but understand how that then has an influence on the real world. And so this is one example of that, where there was a demonstrated digital twin produced looking at critical infrastructure in the UK and how that might be exposed, and how the interconnectedness between that different critical infrastructure when it's exposed to climate-related risks. So, for example, if you have a big flood event, then that might impact. In fact, this has even happened. There was a big flood event in 2007 in Gloucestershire, which came very close to taking an electricity substation offline. That electricity substation provided the electricity to 500,000 local homes and businesses, but it also provided the electricity to the local sewage treatment works. So you start to get this knock-on impact. It's not just the electricity, it's the sewage treatment, it's the telecommunication systems, and how do these all interconnect. And so there's a lot of interest in building digital twins to understand those interconnections. That's just one example. And then how can you make them more resilient? In the climate context, another area where there's a lot of interest in building digital twins, and it's already very advanced, is in terms of how to manage electricity systems with an ever increasing amount of both intermittent generation in terms of renewable energy, but also intermittent demand in terms of when there's much more electric vehicles on the system, for example. Lots of interest in digital twins. And then the final area is, how can we start to be bringing machine learning processes into the climate modelling world? And an obvious area is, where can you use machine learning processes to improve the parameterizations of those climate models that I was describing. But there are other areas as well in which there's a lot of interest in using machine learning processes. Could we replace the entirety of these climate models with data-driven models instead? There's some interest in looking at that. And the other area where I'm very interested, and I think there's a lot of opportunity for using machine learning, is essentially in terms of building emulators that allow, so at the moment, that massive modelling effort that I described is all focused around using a coordinated effort to model a set of future scenarios, as is described here. But of course, any policy or the real world inevitably follows a different scenario. So could you actually take the output of these different climate models under these scenarios and use that effectively to train a machine learning based emulator that then allows you to look at any scenario, not just the ones that have been explicitly modeled. So there's different ways in which we can be looking to use machine learning. Yeah.
How does this all translate to
So when we're looking at microclimates, so anything, I mean, at the moment, in these kind of classic models, as I described, the grid scale of these models is, you know, maybe even 100 kilometers. And so the output of those climate models will be just uniform over that 100 kilometers. But of course, within 100 kilometers squared, there's going to be lots of different microclimates, and they could be really, really extremely different. If you have in a mountainous region, for example, then, you know, very short distances can make a big difference. So that's then a whole other area of interest, which is how do you take the information that's come out of these models and then use that to try and help inform what's happening at a much smaller scale. And actually, I'm going to describe some of the ways in which we're trying to use, again, machine learning to do that downscaling, we call it. So you take that larger scale information and then use that as input to either a physics-based model to create the downscaling, or can you use a data-driven approach to say, well, if I have these conditions, what does that imply for this, these larger scale conditions, what does that imply for this microclimate? And use the maybe historical observational information for that microclimate to be able to do that mapping. Okay, so I'm going to give you just a few examples of some of the various projects that we're involved in Cambridge in terms of progressing some of the involvement or the use of machine learning in various different aspects of climate modelling. And this is the first set of projects that we're involved in. These are all projects that are, they're big consortium projects. So they involve scientists from multiple different institutions. Our role in Cambridge on this set of projects is that we're providing the research software engineering support for those different science teams. And so just to give you a flavour of some of the different things that people are looking at. These are predominantly focused around improving the physics bit of those climate models. The DataWave project is focused on developing new parameterizations for a really important process of climate models, which is called gravity waves. So gravity waves are basically, imagine that you have a mountainous region, the wind blowing over those mountains, that can create disturbances that propagate up into the atmosphere. And actually, and this happens in a lot of different atmospheric processes, the disturbances happen on quite small scales, but then the downstream impact of those disturbances, because they affect the buoyancy, the pressure patterns in the atmosphere, that can have a much larger scale influence and actually drive huge global scale changes in the circulation. They're really important. It's a small scale process that can have a big, large scale impact. So it's really important to get those processes properly parameterized in the models. In fact, there's something called the quasi-biennial oscillation, which is literally in the tropical area, all the way up through the atmosphere. On a 2-year cycle, the winds literally change between going in an easterly direction to going in a westerly direction. And the key process that results in that oscillation is these gravity waves. So unless you get these gravity waves right, you don't get that oscillation that we observe in the winds in the tropics. So it's a small scale thing, has a large scale impact. And so this project is particularly looking at how to develop machine learning based processes. The picture that you see in their logo has got a balloon, and there was Google funded this project that was going to be using balloons going around the world to help do internet coverage around the world. I think it got cancelled after a few years, but the data set from those balloons is being in part used to train these machine learning methods, because where those balloons moved gives you information about these gravity waves. So that's one thing that's been looked at. I mentioned sea ice as being something that's really challenging to represent. And one of the reasons it's so difficult to represent is because sea ice, the key processes associated with the evolution of sea ice happen on many, many different length scales, but they also involve a large amounts of different physics. And so it's challenging to represent all of that numerically. And so this is looking at, again, how can we produce data-driven sea ice models? And so there's one challenge in terms of the development of the machine learning approaches themselves, and then there's another sort of computer science challenge in terms of how do we actually implement that in terms of the modeling, numerical modeling itself. And you can see that at the bottom of this slide, I've highlighted some of the software engineering challenges in terms of how do you parallelize the code associated with these, and how do you get as I described, many of the climate models that these parameterizations are fitting in are all Fortran based. So how do you get good interoperability between a machine learning code that has been developed probably in Python and then talking to the underlying Fortran based climate model. So those are two parameterization based models. The next example is this project called Lemon Tree. And this is really interesting. So this is looking at a different aspect of the climate system, which is the biosphere. So all the kind of plants, and in particular on the land, it's looking at the terrestrial biosphere. And so one of the things that we know is that as you change the climate, then plants do evolve. And so if you have larger levels of carbon dioxide, plants grow better, or they can adapt to changed climate conditions. They're not completely stationary. So how do we represent that evolution in terms of the modeling itself? And so that Lemon Tree project is trying to develop a new class of model component for that terrestrial biosphere that includes some adaptive properties. And it's looking at developing an entire model component for that based on machine learning principles and all coded up in Python. And then the final example of M-squared lines, so you have these different models representing different parts of the climate system, model of the atmosphere, model of the sea ice, model of the terrestrial biosphere, and you've got to find ways of coupling those together, because the atmosphere affects the oceans affects the climate, the atmosphere, and all of them affect the biosphere, the sea ice as well. And so how can we better connect and couple those different elements? And one of the things that that project is particularly focused on is developing interpretable machine learning aspects of this, so that we're not just implementing some kind of black box machine learning process, but we understand physically what's happening. That has two advantages. One is that it gives us greater confidence in the results, because we can explain what what the physics behind it has been. But actually, it also enables us to better understand from at a more fundamental level some of the key physics that's actually happening, and that helps us to answer some of the key climate-related questions as well. So that's some of the project. Oh yes, go on.
To what extent do you believe that these models will be effective?
Well, all I can say is, I mean, No, of course they're not. But they have been the modelling effort to date has been influential in the albeit limited international response on climate change. So the most recent big climate conference that happened in Glasgow last year, the outcome of that was something called the Glasgow Climate Pact. And the Glasgow Climate Pact was like a sort of, no, I can't remember, 10-page document or something that all countries signed up to. But it was basically an articulation of what had been said in the IPCC report. So the countries all, you know, it said, if you read the text of it, it said, you know, that there was a recognition that the impacts of climate change were happening in every region of the world. That was a direct quote from the IPCC report, a recognition that to keep temperatures well below 2 degrees with an ambition to keep them below 1.5 degrees required halving of emissions, or basically reduced by 45% by 2030 globally, reaching net zero, etc. So all the statements that have been in the IPCC report, which came from the climate modelling, did make their way through to the political agreement. So it's influential in that respect. And pushing the boundaries in terms of improving our future projections is really important for that politics, because one of the areas that's currently an area of greatest uncertainty, as I was highlighting back here, is how future projections at a local level, if you're a politician for a particular country, then understanding what the risks for your particular country are in terms of in particular extreme events is quite a big motivator for actually putting in place policies, rather than this more abstract of 1.5, 2 degrees. So I think it's quite important. It's not going to solve the problem, but it's quite an important element. Right, I'm going to just, in the last 50 minutes, just run through a few examples of some of the work that various people in Cambridge have been undertaking on other aspects of this, where we've been deploying different machine learning based approaches. To give you just a bit more insight into some of the things that we're actually using. So I've taken 4 different aspects of the climate system where we've been working on: sea ice, which I've already mentioned, heat waves, which is a bit pertinent right at the moment, oceans, and flooding, basically. So the first example of sea ice, this is a paper that we had that came out a couple of months ago, if anyone's interested in looking at the details of it. And so, as I've already described, sea ice is something that's very challenging to predict. It's important to predict, though, as well. And it's a part of the climate that's seen some of the greatest change. So the graph that you see on the bottom left there is the extent of sea ice in the Arctic, measured by satellite data. And I'm showing the September extent. So that's at the end of the summer melt season. That's when the sea ice is at its smallest extent. And you might have heard in the news at times people talk about being able to navigate the Northwest Passage, because it's areas of ocean that are now open and not covered in sea ice that didn't used to be, that mean that you can start to be able to navigate through them. So there's been a massive change over the last 40 years in the amount of sea ice. And literally, if you probably can't read the numbers, but the amount of sea ice coverage has halved essentially over the last 40 years. And that's a huge area of decrease. Across that whole period of time, an area about the size of India has disappeared in terms of the sea ice coverage. And that has a huge knock-on impact, actually. This is part of the coupling processes, because normally when that sea ice was there, then sea ice is a very reflective surface, so it reflects a lot of the sunlight. And when it disappears, then the sunlight is then absorbed into the oceans, and the oceans heat up, and you get this feedback effect of getting more melting as a consequence. And it can also have a big impact in terms of broader weather patterns and so forth. So understanding the coupling processes is really important. In terms of the forecast side of things, what we were interested in doing was seeing whether we could forecast sea ice over the next 6 months using a data-driven approach. And the way in which we were looking at that is basically turning the forecasting into a classification type problem. So what we were wanting to do was be able to do that forecasting in terms of classifying whether in a particular grid box there was either open water, marginal ice, or sea ice. And that was the kind of the classification that we were trying to undertake, rather than producing a continuum, instead creating that forecast in terms of those 3 classes. And so we had data to input in terms of current sea ice concentration, and then a number of other climate variables that we thought were relevant to the future prediction of sea ice. And that is things like the temperature and the pressure and so forth. And so the way that we were doing this, we were using a unit type approach. We used some of the climate model data to help do some of the pre-training. And then we produced a simulation associated with that. And our benchmark to compare against was the dynamical forecast, the traditional physics-based forecast. And as I say, if you're interested in the details of any of that, then take a look at the paper that came out in the last couple of months. But the key thing was that this purely data-driven model was able to outperform the traditional physics-based models, at least with a lead time of at least 2 months. So then the second example is one related to heat waves, and in particular more related to the microclimate question that I got. So the challenge here was, so this is on the left-hand side shows you the raw output from all the different climate models, looking at surface temperature around the world. And what you can see is that each of the different models, in terms of the exact pattern that they have globally, are a bit different. So there's not, there's quite a lot of variation between the different models. So if you're looking at a particular location, you get quite big differences. And so the question is, on the basis of all that information, how do you get to a projection of what extreme heat might be at a particular location? And so one thing that, one challenge is that if you look over the period at which we have actual observations and run these climate models over the period that we have actual observations, there are often big differences between what the climate models predict for a particular location and what the actual observations are. So there are effectively biases in the model. So the first question is, can you find machine learning approaches to help correct the systematic biases in the climate models at a local scale? And then the second question is, can you find a machine learning approach to, in a informed way, look at how can you weight the different climate models to create some, how do you determine which climate models have greater fidelity, for example, and how do you combine them together? Because traditionally, what's been done in the climate world is just to equally weight each of these models and create a multi-model mean, which does, it's been shown to have more skill than just looking at any individual model, because you get some cancelling of errors, but you ought to be able to do something smarter than that. So that's the challenge. And it's particularly a challenge in terms of looking at projections of extreme events. So where's a good place to start on this? If you look at the bottom picture on the left-hand side, that's looking at the distribution of maximum temperature in June, July, August for a particular location. It happens to show Chicago. And you can see the actual observations for the period 1980 to 2019 are shown in blue, and that's the distribution of temperature. There's you can look at the over that June, July, August period. On average, the maximum temperature was in Chicago was about 30 degrees, but there are some very hot days and some much cooler days than that. If you look at one particular climate model and what it shows for that temperature over that time period, it happens to be one of the UK Met Office climate models that's shown in red. And you can see there's a systematic bias in which it systematically predicts lower than the observed average temperature. And the distribution's just slightly off. If I looked at a different location, then the biases would be in a different direction. So the question is, how can we find ways of correcting for this? And and in particular, you can see that it's not just a case of correcting the actual shape of the distribution changes. So you need, if you're interested in understanding how to correct for the extreme events, what you wouldn't want to do is correct for the average conditions and shift the entire distribution exactly as is, because then you would likely get the extreme conditions very inaccurately represented. And in fact, what's traditionally done in the climate science world is to correct the mean and maybe the variance, but that can really distort the extreme events. So one thing that we're trying to do is use machine learning methods to improve that. One of the ways in which we're trying to do that is use Gaussian processes. We're particularly using approaches that focus on ensuring that we get those extreme events better represented. Okay, and then very quickly, the last couple of examples, looking at creating simple representations of ocean circulation and how we can use information from the existing state of the oceans to step forward a model to predict a future time step. Essentially, one way that we can do this is take the existing climate models as our input training data set and see whether or not we can use those to train basically an emulator in order to be able to time step in a more computationally efficient way than running the full climate model from one step to the next. And that's one area that we've been looking at. It turns out that it's really quite challenging to do that because essentially you've got to find a way, I mean, your approach has got to be learning all the key physical processes in order to be able to do that time stepping. And it's not straightforward, but it's that's the sort of holy grail of some of these approaches. And similarly, actually, in terms of the hydrological forecast, the flood forecast. So what we're trying to do here, similarly, is understand what some of the key inputs to predict future flooding might be, and then essentially train a model in order to do that prediction. And so the sorts of things that we're looking at in terms of inputting would be the amount of rainfall, perhaps the amount of rainfall over the previous week or couple of weeks, because it's not just the immediate rainfall, but how much is built up, how waterlogged the land is, for example, as well as aspects to do with the temperature. But then it also turns out that in a particular location, as you might imagine, the amount of water that's extracted by water companies, for example, has an important, or what exactly the flood defense is in a particular river, might be, has an important impact as well. So how can we start to include variables that would then be able to learn and represent some of that information as well? Is again part of the way in which we're trying to not only account for the physical processes, but the wider set of processes that have an implication in terms of flooding. And then finally, the final stage in terms of providing then information that can support decision making is how can we then take that information that we've got in terms of the climate related variables and then add on the extras. So I've just started to give some examples of that on the flooding, but how can we go even further to then add on the information that then gives information to inform the actual changes in the different things that would be important to decision making. So for example, in a heat wave, what's then the information that shows how energy demand might change because of more air conditioning use? Or what's the information that would then tell us how many health impacts there might be of high heat waves? And so that is potentially also another aspect in which we could use machine data-driven approaches by looking to learn the relationships between the extreme weather conditions and what the downstream impact of those extreme weather conditions might be. So that, I hope that, I mean, it's such a huge topic, it's difficult to dive into any particular details of any of it in a short amount of time. But what I wanted to do was just give you a sense that there's huge opportunities in this really big area to do a whole range of different types of machine learning approaches to really make step changes in the level of understanding that has really important real world implications associated with it. So I'm going to leave it there. Thank you.